Hi, this is Leanne.
Hi, my name is Angie.
Hi, this is Yue.
Hi, I'm Chase Scott.
Hi, my name is Ethan Oman.
My name is Matthew.
And I'm Rachel Tan, and this is our project, Walk Walk Fashion Baby, where we created a model that generates fashion t-shirts. So our project can be split up into around 4 different parts. First of all was data acquisition, which was a really long and tedious process. After that was segmenting the data sets of t-shirts that we found. And from there, we generate our t-shirts, and then we finally output a t-shirt with some style transfer applied to it. So during the data acquisition stage, we first attempted web scraping, and I found that web scraping was very, it required a lot of time. That ended up not being as efficient as we wanted it to be. So we ended up relying on we went through 3 different data sets. The first one is Fashion MNIST, and the image on the right is Fashion MNIST. The second one is with the Grigoriev dataset, and the third is with the Agarwal dataset. But first, we used the Fashion MNIST dataset while waiting on some other datasets, which Ethan used to train his model initially. Afterwards, when we were looking at more ideal t-shirts that were firstly in color, 2 were easily visible or flat, and 3 had a clear black background or preferably didn't have a model in the image. With Grigoriev dataset, all the pictures were laid on some kind of surface, and it wasn't always flat, or the surface had a lot of noisy colors, as you can see in the second example of the Grigoriev dataset images. And this dataset only contained about 5,000 images, and of those 5,000 images, there were 950 t-shirts. But the Agarwal dataset ended up being a lot ideal for what we needed. The Agarwal dataset had a total of 44,000 images. Of those images, we had around 10,000 t-shirts. And after going through and the dataset and picking out the ones that segmented best, we had around 6,500 t-shirts.
So for image segmentation, we use Python's OpenCV library to extract t-shirt from each image. Initially, we use a simple code where it performs Gaussian blur, edge detection, medium filtering, contour drawing, and then masking. The result filter out most of the background, but as you can see in figure 8, there are still some unclean edges. Then we research more into how to improve OpenCV code, and we found this example where they use a polygon approximation to extract out this receipt. So we set the polygon edge number to be roughly 10, which is what a typical shirt would have. However, our code does not detect the specified value well. So then we read more about OpenCV thresholding. We try out our data set with simple thresholding and adaptive thresholding. The performance of neither technique is well enough to be generalized over our data sets. So finally, we try out Kenny Edge technique before drawing out our contours. Since Kenny Edge gives this more detailed edge, it might increase possibility of finding a better contour. However, because it's giving us or is finding more detailed edges, they also most of the time overemphasizes the detail in the image. So it's not ideal for finding a t-shirt.
So to start off image segmentation, we try to use polygon estimation first. The reason why we do this is because it creates a nice bounding box for the shirt, as well as being fast to train. Now the only issue with this method is that it comes with a loss of quality. As you can see on the right, my model predicts a good outline of the shirt and a rough shape. However, if you look closer, it starts to lose a lot of the fine edge details. Now, my model was initially trained using Detection 2 from Facebook. I used the mask RCNN on the Coco dataset as a base, and further trained it on shirts using ResNet 50 as a backbone. Now, while my model does a good job predicting on shirts on static backgrounds, it doesn't do well when the shirt is being worn by a model. I call it the guillotine model for a reason. As you can see, the model on the left only has its head cut off. So the image on the right, which is the prediction, is not ideal for our GAN dataset. However, I thought if we used UA's grab cut algorithm, we could further improve the right prediction and then actually have something acceptable.
So we further inspected the OpenCV library, and we find out that actually OpenCV offers a grab cut algorithm which can either accept a rectangle or a shaped mask to extract the foreground nicely for us. We try out with the rectangle first. We use the EULO V5 object detection model to detect the region of the t-shirts and feed the information of that rectangle into the grab cut. As we can see here, it can do a quite decent job for all the t-shirts only images, which adds up more than 2,000 segment t-shirts into our dataset. However, when it comes to the t-shirts for wearing by a model, the result is not so optimal because GraphCAD will take the included human body as foreground as well. How to solve this problem? An idea something struck to us is that we can actually use detection tool to generate the shaped mask for us and apply that to the GraphCAD. We try out with this idea immediately and find out that the result is quite promising. Eventually, with the combination of detection tool and GraphCAD, we are able to segment the t-shirts nicely off from the models. This again adds up to another more than 4,500 segmented t-shirts into our data set.
A big component of our project was using generative adversarial networks to create images of t-shirts. A GAN is simply built out of two models, a generator and a discriminator, with a generator attempting to create an image from random noise, and a discriminator judging the images as real or fake based off a set of real images. GANs are incredibly difficult to train because of the complexity of handling two models that work off of each other. This trade-off between models leads to many different tuning techniques that have various levels of success. The most interesting techniques we used include two-time update rule, which is simply selecting different learning rates for the generator and the discriminator. Another one is label smoothing, which is taking the hard-coded one value of real images and softening it to 0.9. The other ones include spectral normalization, which is just a normalization tactic, adding any kind of regularization to the generator, particularly L1 loss, or even just trying to create a smaller image. Of course, even within these techniques, they have variant levels of success. L1 loss in the generator had the biggest impact on improved consistency. However, as you can see from the images, spectral normalization, choosing different learning rates, and label smoothing all had some impact on the performance.
Now for the next portion of our presentation, I would like to briefly discuss two more models that we use for t-shirt generation. The first of these two is called the wash scene GAN, which is used in practice to increase the training stability of generative processes. Now, as a group, we hypothesized that utilizing this increase in training stability might actually help us to produce t-shirts with designs on them rather than just producing monochromatic t-shirts. Now, the wash scene GAN we found actually was less consistent in producing structurally sound t-shirts than the deep convolutional GAN. However, our hypothesis was slightly correct in that the wash scene GAN did produce t-shirts with designs on them. However, they came with their flaws. Mainly designs were just random amalgamations of colors put in the middle of t-shirts, or other designs just had random missing patches in them. So the third generative model that we used was called the variational autoencoder. The variational autoencoder is effectively something that learns a generative latent space in which one can generate samples from. For the purposes of our problem, we chose to use a variational autoencoder that had a 512 dimensional latent space. Now, the outputs of the variational autoencoder were actually extremely proficient in learning the general form of a t-shirt, which makes sense as the variational autoencoder seeks to minimize the difference between generated images and real images. And so finally, just manipulating the latent space a little bit led us to realize that our learned autoencoder effectively changed the color and size of our t-shirts.
After the t-shirts are generated, we decide to generate masks for the t-shirt that we are going to have a style transfer model. This picture shows a general idea for the overall process. We used two style transfer models in our project. The left-hand side one used the TensorFlow Hub style transfer module. It is faster, and it is easy to tell the style of use from the transferred image. The right-hand side one used the VGG19. Compared to the previous model, this one takes more time, but it contains the feature for both content and styled images. We also try to generate our own style. We crop one part from random selected t-shirt and combine those together to create a new style. We also try to blend those parts together to create a new style. The third one we try is to clear the blending image a little bit to create a new style. The table right here shows the result for the orange t-shirt with those three styles and two models. However, the overall result doesn't seems to be so impressive as using the artwork. The further step we can take is to generate some more clear and interesting style that we can test with.
So in conclusion, we are proud of our final product and the work that went into it. However, there's always room for improvements. What we could have done beforehand is clean the dataset by separating out into different classes. Since our model is very selective on which types of images it wants to work on, if we did this beforehand, we could have saved much more time and trained the GANs for longer. Additionally, we could have also explored SOTA generative models for t-shirt quality improvement, as well as explore other types of style transfer. However, with that being said, I'd like to thank you for your time in watching this presentation, and I will leave you with some of the outputs that are less than ideal. Thank you.